All right. We are going to do a two-sided test today. So when the alternate hypothesis is not equal to, then we're going to talk about what the power of a test is. And then we're going to actually compare the relationship between a confidence interval and a test. So yeah, there's kind of a lot today. So let's run through quickly a two-sided test. All right. According to the Centers for Disease Control and Prevention website, 50% of high school students have never smoked a cigarette. Taeyeon wonders whether this national result holds true at his large urban high school. For his AP Statistics class project, Taeyeon surveys an SRS of 150 students from his school. He gets responses from all 150 students, and 90 say they've never smoked a cigarette. What should Taeyeon conclude? Give appropriate evidence. So is this a means or a proportions problem, guys? It's biased because people aren't going to tell you the truth? Well, hopefully you do an anonymous survey so people will be a little more comfortable, but they might lie. All right, you can talk about that in your results. So the null hypothesis is that the true proportion is 50%, okay? But Taeyeon wonders if this holds true, meaning he's not suspicious of more or less. He just wants to know, is it different from the national result? So this is now a two-tailed test, okay? P is still the true proportion of teens who have never smoked. This is still a one-sample Z test for P. We're going to check all the things. What's the first thing that we always check? And SRS does mean simple random sample, all right? So yes, they took a random sample. Then we're going to check 10%. He surveyed how many kids? Okay, 150 is less than or equal to a tenth of all the students at his high school, which is like at least 1,500, so I think we're good. All right, and then for large counts, we're going to do N times P from where? Yes, always use the null hypothesis. So we're going to do 150 times 0.5 and 150 times 0.5. All right, yes, you should write 75 twice, all right? Yes, it is greater than or equal to 10, so we can assume normality. Okay, for the do step, we are going to do a z-score. We need a test statistic. This is a proportions problem. The first number up is a p-hat. What's the p-hat in this problem? Good. It's going to be 90 out of 150 for my p-hat. Okay, we're going to subtract the null hypothesis. All right, so I'm going to subtract 0.5, and I'm going to divide by the square root of 0.5 times 0.5 over n. What's n in this problem? Good, 150. Okay, this is going to give me my z-score of 2.45, and here's where it's different. Okay, should I just shade the positive side? No. Because it's not equal to, we actually want this to be plus or minus here. All right, so I'm going to shade 2.45 to the right and also negative 2.45. Okay, so when I do my p-value, I'm going to do norm CDF, and I usually just do one side, so I'll do the upper tail, the 2.45, all right, up to a big number, mean of 0, standard deviation of 1, and then I have to do what? You have to double it, exactly. So it was 0.0071, but we need to multiply that by 2 to get the area under both sides, which is 0.014. All right, and our concluding sentence. So the only new thing, you guys, is plus minus, the not equal to on the alternative, and double your p-value after you find one tail. All right, and then use the p-value that was doubled. Okay, it is less than 0.05, so we reject the null, which means we have convincing evidence that the proportion of all students at Taeyeon School who smoke, or who would say that they have never smoked, differs from the national result of 50%. Now, we don't actually know greater than or less than. Even if our sample was greater than or less than, it was greater than, all right? We don't know that. We just say in the concluding sentence that we have convincing evidence that it's different. And this is who would say. So we did include that in our conclusion for kind of the bias that you're thinking of, all right? Now, confidence intervals. It's been a while since we've calculated a confidence interval. It looks like this, in case you forgot. This would be like the formula for it. All right, and you could just plug it into your calculator to quickly get 0.522 to 0.678. Guess what? We can relate these to our test, okay? Our confidence intervals and our two-sided tests are friends, okay? Now, what this means is that an alpha significance level of 0.05 is friends with a 95% confidence interval. As long as it's a two-tailed test, only the two-sided test does this work, all right? So you know how our null hypothesis just a second ago was P is 0.5, and our alternate was just like it's not 0.5, it's not 50%. Do I have convincing evidence when I look at the confidence interval that the null, that I would reject the null? Yes. The entire thing is above 0.5, okay? Which gives us more information, the significance test or the confidence interval? The confidence interval actually gives us more information. So we actually can conclude that Taeyeon's school maybe have more people who say they would not smoke. Is that what it was? Okay. It's all above 0.5. All right. So they go together. So here is the exact same thing. So this only works with a two-sided test. All right. And we have to have the same percentages here. So a 95% confidence interval will give us the same information as a 5% significance test. And a 90% confidence interval will give us the same information as a 10% significance test. And for 99, that goes with a 1%. Okay, so those go together. So let's look at like a question they might ask you. All right, this shows the Minitab output for a confidence interval for some kind of restaurant worker. All right, explain how the confidence interval is consistent with, but gives more information than the test. So hard to read this, you guys, but it's got P is 0.75 versus P is not 0.75. So this is my null hypothesis and my alternate hypothesis. Then they gave us a 95% confidence interval. And I can look, is the null inside the interval in this one? It actually is. It's included. So that means, would I reject the null or fail to reject the null? I would fail to reject the null. At what significance level if this is a 95% confidence interval? Yeah. At the 5% significance level, I would fail to reject the null because it's in the interval. It's included in that 95% interval. All right. Notice they have a z-score and a p-value, and notice the p-value is not less than 5%. So that gives us the same information. Okay. Okay, power of a test and type 2 error. I'm going to explain power, all right? I'm going to try to show you the math behind it. The main thing is that you just understand the definition of power. Write this definition down. It's very important, all right? The power of a test is the probability of correctly identifying the alternative hypothesis as true. So if the alternative's true, it's the chance we actually get that the alternative is true. This also means avoiding a type 2 error. What's type 2 error again? Exactly. Failed to reject when we should have rejected. I want to avoid that. I want to correctly reject the null when I'm supposed to. All right, this definition, you must know this definition, okay? So we're going to use the potato chip example for me to explain this a little further, all right? So remember, we're going to reject the truckload if more than 8% have blemishes, right? What if we actually know the truth, okay? Let's say we know that the true proportion of blemishes is 11%. So we should reject the null, all right? I want to reject the null because it is really actually greater than 8%, okay? Well, let's just read this real quick. Okay, we've got this. Based on a round table of 500 potatoes, we already know that, 11%. In this case, a particular type 2 error is to fail to reject, right? We want to avoid that. And here's our two sampling distributions. All right. So we have two sampling distributions I want to talk about. This one is based on the null, which is how we decide whether or not to reject. Okay, we always base it on the null being true. We're assuming it's 8%. All right. And so I filled in 8% right here, and I actually calculated these little standard deviations, assuming that 8% is true, by doing the formula for standard deviation for random sampling. Okay, that's how I got these tiny little adorable numbers right here. That's just the spread for your random sampling for a proportions problem. All right, and then this is based on the truth. Okay, so for the truth, we actually know 11% are blemished. But you're going to get different samples, right? Every time you take 500 potatoes, you guys agree it's going to vary from sample to sample, right? Every 500 potatoes. So this one's based on the truth. So this one's standard deviation comes from the 11%. They're still very close standard deviations. All right, and I filled all those in. So if I reject the null at the 5% level, okay, we base all of our math on the null hypothesis being true. So if I have 11% blemishes, that falls in the reject region, but I'm going to get different random samples. Okay, so every sample is different. I might get one that's really low. I might get one that's really high. All right, so if I reject at the 5% level, I can actually find what number, like what percent of blemished potatoes is going to get rejected. Okay, by doing inverse norm, area 0.05, you don't have to know this for the test, okay? Mean of 0.08 and standard deviation from this formula right here, okay? And if I plug that in, I'm actually rejecting at the 10% level. So even though the truth is 11%, I base my random sampling on the 8%. I don't know the truth, right? So I'm basing it on the 8%. Anything 10% or above is getting rejected. Okay, but there could be a sample that's 9%. You guys agree? That doesn't get rejected, even though the truth is 11%. So that means if I base it off my truth, here's how I find the power. Well, I'm calculating it at 10%. So anywhere 10% or more is going to get rejected. This is the likelihood that I will correctly reject the null. That's the power of the test right there. How would I find that area? Well, I would do norm CDF, because now I want the area under the curve. Oops. My lower bound is that 10%. I'm cutting it off at 10% up to, obviously, 1 is the highest you could go. Okay, my mean on this one's 11%, and my standard deviation on this one is this guy right here from the random sampling. And if you did that, you get a 76% chance of correctly rejecting the null. Let's say you didn't understand anything I just did right there. It's totally okay. All right. You need to know what the power of the test is, and it's the likelihood that you will correctly reject the null. All right. I did it mathematically for you based on our null and then based on the truth, how they're finding the power. Okay. That's how they're finding the power. But you just need to know what it is and how to interpret it. So first of all, alpha, you guys have seen this. This is your significance level, right? This is like your 5%. This is the chances of making a type 1 error. All right? You need to know this. I would write this down. Significance level is also the probability of making a type 1 error. Okay, what's a type 1 error? Yes, when we reject the null, but it was actually true. So there's always a fixed % chance that you're going to reject the null, but it's actually true, because when you have random sampling, they vary from sample to sample. You might get one of those weird high samples. If the truth is 8%, you might get a high sample. All right, so you might accidentally reject when you shouldn't have. Okay, that's the likelihood of doing that. Okay, now B is the probability of making a type 2 error. Beta, all right? That's the probability of making a type 2 error. Now, the power we want to avoid. Power is 1 minus beta. I don't want to make a type 2 error. A type 2 error is failing to reject when we should have, right? So the alternate's actually true. So the power is 1 minus that. So if I have a 20% chance of making a type 2 error, I have an 80% chance of avoiding that and correctly rejecting null, which is what I want to do if the alternate is true. All right? And the probability of a type 2 error is 1 minus the power. They're complements, okay? They add to 1. All right, I would also write this down. There are 3 ways to increase the power. You want to increase the power, right? I want to reject the null if the alternate is true, all right? Like in the potato problem, if it's really 11%, I don't want to make bad potatoes. I want to reject the truckload. One way to do it, to be more accurate, would be to increase the sample size, right? So you could increase n. You can also increase alpha, your significance level, right? If I made my cutoff 10%, right, for how far I reject, well, then I'm more likely to reject, right? If my cutoff's 10%. And this last one is called the effect size. Increase the effect size. In other words, if the truth is if the null is 0.08 and the truth is 11%, what if there's actually 25% bad potatoes? Am I even more likely to reject the null if it's further from the truth? Yeah. If I have 25% bad potatoes, I'm super likely to reject my null. So if your difference between the null and the truth increases, then you're more likely to correctly reject. Obviously, I don't know if you can always control that, all right? But there's a big difference between the truth and the null. You're more likely to reject. Are you more likely to avoid a type 2 error if you inspect many potatoes or just a few? Many, okay? Is it easier to reject the null if alpha is 1% or 10%? 10%. The bigger the significance level, the easier it is to reject. Is it easier to detect a bad shipment if the null was 0.08 if the truth is 9% or 90%? Yeah, if there's a lot of bad potatoes, you're probably going to reject it, okay? All right, which is more serious for the potato chip producer in this setting, a type 1 or a type 2 error? So a type 1, you would reject a good truckload, okay? You'd waste the potatoes. A type 2, you're going to make really bad potatoes and like sell them. So it's probably a type 2 that you want to avoid. So if you want to avoid a type 2 error or increase the power, which one of these should you use? Yes, the highest significance level. All right? Tell if each of the following would increase or decrease the power of the test. Change the significance level to 0.1. Increase. Take a random sample of 250 instead of 500. Decrease. Decrease. Insist on being able to detect that P is 0.10 instead of P is 0.11. Yeah, that makes it worse. So if you change the truth to this, I don't know how you can just change the truth. All right, but if you change the truth to 10%, that's closer to the null. That doesn't help. All right, that decreases the power of the test. All right, you guys, there is no worksheet today. Yay for the long lesson. This was better than I taught it several years ago. And there's your homework.